Hello everybody. In the last two classes we had discussed synchronous and asynchronous counters, up and down counters with modulo number 8, and we had seen how it works even for modulo number 16, right. And we can of course understand that how it will work for modulo number 4 also, okay, though the basic circuit that we had discussed for 8 and one example we had seen for 16, right. So, this is where the the modulo number was in the integer power of 2. So, in today's class we shall look at some other modulo number like modulo 3 counter, modulo 5 counter, and then we shall look at the effect of cascading. I mean, if we cascade one counter with another counter, we can get a modulo number which is, if you just multiply them, then whatever the value, so that modulo number will come up. Okay. So, we shall look at such arrangement. Okay. So, we begin with mod 3 counter. Okay. So, let us see the circuit of one mod 3 counter, right. So, it is made up of JK flip flop, right, and this is synchronous, the clock is fed here, right, and in this B bar is fed here as J input of A flip flop, okay, and A output is going as J input of B flip flop, right, and K input for both the flip flops are connected to logic high. Okay. Very simple circuit, you can see it, right. Now, let us see how this circuit behaves, okay. So, initialized with 0 0, so this is the clock, right. So, 0 0, then at that time your JB, KB and KA is always 1, it is permanently connected to 1, right. So, JB is A, so A is 0 means JB is 0, right. And what about JA? JE is B bar, B is 0, right. So, this is 1, okay. JA is B bar, right, it is fed back like this. Okay. So, this is 1. So, after the clock trigger, what will happen? So, this is 0 1, right, JB. So, it will remain at 0, and this is 1 1, it will toggle from 0, it will come to 1. Is it clear? From 0 0, we have come to 0 1. We are analyzing a sequential circuit, right. Now, when it is like this, so JB now, because A has become 1, right. So, JB is 1, KB is always 1, JA since B is still 0, it remains at 1 and this is 1, right. So, next clock trigger, both the flip flop toggle. So, 0 becomes 1 and 1 becomes 0, right. This is the case. After that, what happens? JB is A means the 0, this 0 comes here, and J is B bar. So, B is 1, so it is 0. So, this is 0 1 and this is 0 1, okay. So, after clock trigger, what will happen? So, both of them will get 0. So, we are having 0 0, 0 1, 1 0, 0 0. Okay. This is visible in the timing diagram also. So, once it goes to 0 0, the cycle will continue, cycle will repeat after at 0 0, after 0 0, 0 1 will come and 1 0 will come. Okay. So, this is the mod 3 counter that you can see, and in this case, if you take the output from flip flop B, okay. So, every 3 clock pulses, it will remain high for 1 clock period, isn't it? So, regarding the decoding logic and all, this B flip flop output directly gives you the output that a count of 3 has taken place, and it will remain high for 1 clock cycle, right. So, we do not need any separate circuit for that, okay. Is it clear? So, if we put this thing as a mod 3 block like this, right, within which we know that this is the circuit, this is the way the circuit behaves. Okay. So, 0 1 2, again 0 1 2, this is the way the count goes on. If that is the case, then let us see if we connect a mod 3 and mod 2. Mod 2 you all know, right, 2 4 8 16, right. So, mod 2 means only one flip flop, at its output it is divided by 2, right. So, that is mod 2 counter. So, if mod 3 and mod 2 put together, what happens? Okay. So, there are two arrangements. One, in the first arrangement, first we are putting the mod 3, okay, and the B flip flop which is going high and remaining high only for one clock period for every 3 clock pulses. Okay. So, that is B output is fed as clock to the next flip flop. Okay. That is the mod 2 counter, right. So, in this case what happens? In this case, this is your A and B, which is changing as 0 0 0 1 1 0, right. After that again 0 0 from the previous discussion on the previous slide, right, 0 0 0 1 1 0, right, a count of 3 has taken place, again 0 0 0 1 1 0, again 0 0 0 1, okay, 1 0, because count of 3 has taken place. So, it is repeating, right. Now, every time B goes from high to low. So, B goes from high to low over here, B goes from high to low over here, B goes from high to low over here. So, this Q, which is written as C here, okay, it toggles. Okay. So, it toggles means, so C was 0, initialized with 0, so it becomes 1. So, it will remain 1 till it gets next negative edge of B, right, over here, then again it will become 0 and then it will continue. Is it fine? Now, if you look at these 3 flip flop output together, C, B, A, okay, the unique states they define for these clock pulses that is fed over here, okay, then what are those unique states? So, put together you can see 0 0 0, 0 0 1, 0 1 0, 1 0 0, 1 0 1, 1 1 0, then again 0 0 0, 0 0 1 comes, right. Is it fine? This is what you see if you read it along this line, C, B, A, this way, right. So, you have got 1, 2, 3, 4, 5, 6 unique states after which it repeats. So, what does it mean? It is a mod 6 counter, right, according to the definition of modulo number of the counter. So, it is a mod 6 counter, and what are the counting states? Okay, 0 1 2 4 5 6, again 0 1 2 4 5 6. So, this is the way it will continue. Is it fine? Now, for a mod 6 counter, given the mod 3 counter was giving you 0 1 2 and then again 0, right, you may think that can we get a mod 6 counter which is 0 1 2 3 4 5. So, 6 unit states the count value, then again it becomes 0. Okay. So, this arrangement does not give you the previous arrangement. So, it gives you 0 1 2 then 4 5 6, okay, 3 is missing, right. There are 6 unique states, but it is missing. Now, if you put the mod 2 counter before the mod 3 counter, then let us see what happens. Okay. Since we have already defined A and B, mod 3 counter here as A and B, so we are just keeping it at Q, right. Otherwise, you could write C also, but to avoid, so in this case it is, you know, the order is different, it is A, B, C, so it will be B, A, Q. Okay. So, this is the MSB to, this is your MSB, okay, and this is your LSB. The clock is fed here, the one that which will change faster, okay, is compared to the others actually is your LSB, right. So, and the MSB changes slower. So, B will be the one like this. So, coming back to this discussion mod 2 before mod 3. So, this Q changes in every clock negative edge, right. This negative edges it is changing 0 1 0 1, it is toggling, right. Now, for this mod 3 counter, forget about this clock time being. So, this is the clock, this Q is now fed as clock here, at its negative edge it will behave like a mod 3 counter, right. So, it will give you, so this is one full clock cycle for this particular mod 3 counter, this is another full clock cycle, this is another full clock cycle. So, 0 0 1 0 0 0 1 1 0, again 0 0 0 1 1 0, this is the way it will continue, right. So, one clock cycle, full clock cycle for Q, which is fed here as clock, is 2 clock cycle over there. So, that is why you can see 0 0 is there for 2 clock cycles and 1 1 again for 2 clock cycles like this. Okay. because this Q is a divided by 2, okay, in terms of the frequency compared to clock. Okay, right. Now, if you do the reading from B, A, Q, as I said, MSB is your B and A is Q. So, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and then again 0, 0, 0 is coming. Okay. So, that is the way you have to read the data. Then you can see 0, 1, 2, 3, 4, 5, again 0, 1, 2, 3, 5. So, it is up counter without any skipping any counting value, right. So, this is the way you can get mod 6 counter by cascading mod 3, after that mod 2, and also mod 2 after mod 3, okay, and the counting state value will be like this in each of the cases. Now, let us look at mod 5 counter, okay, one arrangement. Again, there can be many different ways it can be made. So, there could be other than JK flip flop other circuit as well, right. Even with JK flip flop there could be different arrangements. So, this is one arrangement. Okay. So, in this what you can see that Ka, Kb, Kc, right, all of them are permanently connected to VCC, right. Ja is connected to C bar, J is connected to C bar, you can see, right. Jb is also connected to 1, right, but Jb is fed by A, okay. How that happens, how that affects and all that we shall see in the timing diagram, okay. And Jc is fed by A and B, fine. So, this is the initial circuit that we see, and then we shall examine how it behaves like a mod 5 counter, right. So, here the A flip flop will toggle, okay, whenever the inputs are 1 and 1. So, that is the case in the beginning when this C is equal to 1, I mean initialized with all 0, 0, 0, okay, this is all are 0. So, this is 1, right. So, what I have written here this in this notation. So, these are the J and K, okay, flip flop JK inputs are shown for each before clocking. So, this 1 is there, right, and this is permanently connected, okay. So, then A will toggle, right. So, A will toggle means A will become from 0 it will become 1, right. Now, when A goes from 0 to 1, this flip flop does not get the trigger. This flip flop will get the trigger whenever A goes from 1 to 0 at the negative edge of it, because it is a negative edge clock, negative edge trigger, right. So, you can see for B flip flop there is no trigger. B flip flop trigger is for these brown marks, okay, these brown lines that is there, which is associated with the negative edge of flip flop A output, right. So, B flip flop at that time will remain at 1 1 only, okay. Input will remain at 1 1 only and the value will remain 0, okay, for this clock cycle as well, because it has not got any clock trigger. What happens to C, right? C, it is input is A and B. So, the input is 0, right, and Kc is 1. So, this is always 1. So, this is 0 1. So, the output value will remain 0. This is fine. So, after one clock pulse, right, what we can see, the values are 0 0 1. So, this is 1, this is 0 and this is 0, right. So, then this is 1 fed back here. So, this will again toggle. So, from 1 it will become 0, right. So, that is what has happened, okay. And when it toggles, this gets a negative edge. So, B becomes from 0 it becomes 1. So, that is what you have seen, what you see over here, okay. So, this is 0, this is 1, and for this flip flop the input is still 0 1, for which this is 0, okay. Next, again since C is still 0, so A will again toggle, that is what has happened. So, it has become 1, right, and at the unless the negative edge of clock comes, so A comes, B will not change. So, B is remaining at 1, right, and C Before that it is only 0 and 1 because this A was 0, so it is remaining at 0. Now at this point of time, what you can see that A is 1 and B is 1. So this JA is getting 1 1. So in the next clock trigger what happens? Next clock trigger, the C is always getting the clock, right, becomes 1, right, and before clocking, of course, C bar was 1, so A has toggled, right, and there is a negative edge, so for which it has also toggled, for which it has become 0, P has become 0. Now at this point of time, since C has become 1, so C bar is 0, you can see the input of flip flop A is 0 1. So this output will remain 0, okay, and this output is also 0 because there is no negative edge, okay, and at that time A and B both of here this AND input for which it is 0 and this is 1, so this makes the output C 0. So we are coming back to 0 0 0, okay, right. So now if you look at the timing diagram and now these values counting states, so this is 0 0 0, right, 0 0 1, 0 1 0, 0 1 1, 1 0 0, and then again 0 0 0, okay. So this is what you can see over here, right. Again it comes back to 0 0 0. So what is it? 5 counting states and it is sequentially increasing, okay. So it is a mod 5 counter, clear, right. So as I said, there can be other arrangement also, this is one arrangement. Now what we expect to see, the cascading and getting mod 10 counter, and like what we saw for mod 6 counter, where mod 3 and mod 2 were put together one after another. So here mod 5 and mod 2 will put together one after another, and we shall get mod 10 count, okay. That is what we expect, right. And again there could be two arrangement, mod 5 first, mod 2 later, and mod 2 first, mod 5 later. So these are the two possible arrangements. So we shall examine them, and before that we also take note that here C output is remaining at high for one clock period in this particular arrangement, okay. So this can directly give you the signaling that count of 4, that is from 0 to 4, that is this has taken place, okay, 1 0 0 state has occurred, okay. Right. So coming back, so mod 5 followed by mod 2, okay. So in this case the A, B, C, this the first one, these three are mod 5 counter. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0, okay. Then again 0 0 0 is coming, and so on and so forth, right. And at the negative edge of C is fed as clock here, it will toggle, flip flop D will toggle, okay. So that is what is happening at the negative edge of C. You can see that D has changed value. So this is the negative edge of C. So from 0, it was initialized with 0, it has become 1. Again the negative edge of C will come here after the ABC, the mod 5 counter has gone through 5 clock cycles, right, 5 clock edges. So again at that time it is coming from 0 1 to 0, and this is the way it continues, okay. Now if you look at the state values, so 0 0 0 together, that means you are reading DCBA together, okay. So this is, in every case you put the 0, okay, 0, then after that 1, so this is 0 0 1, then this is 1, and it will, this way it will continue. So the first 5 values you can see 0 1 2 3 4. After that what has come? 1 3 zeros, 1 0 0 0 1, okay. So 1 3 zeros is nothing but 8, and this is 9, right. So these are unique 10 states, 0 1 2 3 4 8 9 10 11 12, unique 10 states, right. But the count value, if you convert from binary to decimal and in that manner. So, these are 0, 1, 2, 3, 4, 8, 9, 10, 11, 12. Again 0, 1, 2, 3, 4, 8, 9, 10, 11, 12. So, this is the way it will continue. Okay. But this is a mod 10 counter because of 10 unique states that are there, right. And again, if we for a mod 10 counter, the we would expect that number will be 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, the way the binary coded decimal are represented. Okay. For that, what we need to do, similar to what we had done for mod 6 counter. So, we shall place the mod 2 counter first, okay, followed by mod 5 counter. Okay. So, now this mod 2 counter we are naming it as A, okay, and this we are naming at this mod 5 counter as BCD, right. And so, this A is changing at every clock trigger, right, and after that this A is effectively feeding as clock, okay, sorry, not this one, if there was another like here. So, feeding as clock to the these 3 flip flop BCD, okay, the mod 5 counter, and at this clock edge it will change from 0, 1, 2, 3, 4, 5, okay. So, this is the way it will go on, right. So, now if you look at the state values, so 0, 0, 0, 0, then 0, 0, 0, 1, 0, 0, 0, 1, 0, okay, 0, 0, 1, 1, 0, 1, 0, 0, okay, then 0, 1, 0, 1, then 0, 1, 1, 0, 0, 1, 1, 1, then 1, 0, 0, 0, 1, 0, 0, 1, and finally 0, 0, 0, 0. So, 1, 0, 0, 1 means 9, after that again 0 has come. Okay. So, you have got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0, 1, 2 again it repeats. So, this is mod 10 counter, but where the numbers are sequentially increasing and there is no such jump like from 4 to 8. So, this is called BCD counter and this is called biquinary counter 5-2 counter. Okay. So, 5-2, right. So, would like to see one IC 7490, okay, where we have a mod 10 counter implemented. Okay. So, IC 7490A is one such IC, right, and this IC has got a mod 5 counter over here, right, and a mod 2 counter, right. And you can see there are 2 clocks, this is one clock and this is another clock. This clock is associated with mod 2 counter and this clock is associated with mod 5 counter, right. Now, when you want to make it work like a, so we can make it work like individual mod 5 and individual mod 2 counter. So, for mod 2 we give input here, output here, mod 5 we give input here and we take the output from QD, right. All 3 of them is giving the counting states, but at a count of 5 has taken place, the final signaling if you require in certain sense that decoding of 1 0 0 we can take it from here, okay, right. So, but if you want to work it as a mod 10 counter, we have to cascade one after another, right. So, the cascading can be done again one of the 2 ways that we have mentioned. So, if we want a BCD counter made out of it, so mod 2 counter should be first and then mod 5 counter will be following. So, at that time clock will be fed here, right, the external clock which is getting counted or external event that trigger of which is getting counted, and this QA need to be connected over here, okay. Then the circuit will behave like a mod 10 counter BCD counter, right. And instead if you want biquinary counter, then the clock will be fed here, the external clock will be fed here and this QD will be connected to clock A, okay. Is it fine, right. Now comes there are two other inputs, two sets of other input you can say. This is R01 and R02, right. So, when any one of them is low, okay, so this proper count is happening. I shall discuss little later. So, when both of them are high, then this output is low, this output is low and it will be cleared, okay, all of them will be cleared. So, all the output will become low, okay. So, when both of them are high, irrespective of what is happening over here, right. Now, when irrespective of what is happening means one of them remaining low, okay, please understand that. So, when both of them are high, okay, if one of them this R9 means it is setting 9, so that I will come later. So, one of these input is remaining low, irrespective of what is happening to the other input, the output will be, all these things will be asynchronously cleared, right. And when these two are high, irrespective of what is happening at these places, right. So, this particular 4 flip flops will be loaded with 9, high, low, low, high, QD to QC using preset and clear. So, all of them has got a preset and clear input, right. These two are not required because they will be only getting the clear value 0. So, these two flip flop has got both preset and clear, okay. So, this will be having your what is that called, 9 will get loaded, right. And when any one of them are low, then for both the cases the normal count will happen, okay, based on the clocking arrangement that we are having, either BCD or biquinary if we are looking for mod 10 counter, otherwise normal mod 5 or mod 2 counter it will work. Is it fine? Okay. Again we shall discuss in next class or subsequent classes that why these two inputs and an internal logic gate has been put in this manner, okay. At that time it will be clearer. So, right now if we just need to clear it, we can connect one wire and we can feed it to both of them and we make it high, it will become clear, okay. Later on we will see how this two input and this internal logic gate is helpful, okay, in subsequent classes. Finally, we can extend the way we were cascading in circuits to get higher modulo number from 6 to 10. Now, by connecting modulo 10 counter in cascade like this 7490, 3 of them one after another, okay. What we can get? We can get a modulo 100, sorry, not 100, this is 1000, okay. Please take note of this, okay. Modulo 1000 counter 0 to 999, okay. The count is possible, right. So, whenever this changes by 10, it gets a clock, I mean every 10 changes there will be a negative edge available, and similarly over here and similarly over here. So, that way we can get a modulo 1000 counter, okay, available by cascading, right. If we cascade 2 of this thing, not this one is say there, so it will get modulo 100, okay, 10 and 10, right. Is it fine? So, with this we conclude today's class. Mod 3 and mod 5 counters we have seen require 2 and 3 flip flops, and the way we have designed them is 0, 1, 2, 0 for mod 3 counter, and when we have we are cascading it, we can get, depending on whether mod 3 is there before mod 2 or mod 2 is there before mod 3, we can get 0, 1, 2, 4, 5, 6, 0 or 0, 1, 2, 3, 4, 5, 0. Similarly, for mod 5 counter, we have the states, counting states 0, 1, 2, 3, 4 in the circuit that we have seen, and when mod 5 and mod 2 we are putting them one after another, the cascading cascaded circuit, depending on mod 5 is before or mod 2 before, we have got bi-quinary arrangement or a BCD arrangement, BCD count happening. Okay. And 3 mod 10 counter in cascade gives mod 1000 counter. Okay. Thank you.